Hi, welcome to this video on Project 1, which is all about writing interesting HMMM programs. What I'm going to do in this video is walk you through the problems in the project and give you some hints along the way. The goal of this project is writing interesting HMMM programs. Now, if you go to this URL here and download this file project1.zip, then and unzip that file on your computer, you're going to see these things inside of a directory called project1. Right? So the file project1.pdf is the project specification itself. So that's the file that explains all the problems in the project. And then in addition, you have these files that I call the starter files, and these are the files that you're going to be working on. So you will be fleshing out these files, okay, to solve each of the problems in the project. And then in addition, there is a test script called runtest.py, and this is the file that you're expected to run for each problem in order to test whether or not your solution meets the input and output specification, right? So before you turn in your files, it's highly recommended that you run the test script. So you can be sure that you are producing the right output and so on, okay? And then finally, there is also a file called report.txt that's a template for the report that you're going to be writing. So when you write your report, make sure that you use the given template. Okay. Now, this video is going to be helpful only if you have read the project specification carefully. All right. So before you proceed with this video, please make sure that you've read the project specification and that you understand the problems in the project. Okay. Only then this video is going to be helpful. Okay, so let's start with the very first problem. This is called squared distance, and here you're expected to write an HMMM program called squared_distance.hmmm that takes 4 integers, let's call them x1, y1, x2, and y2, representing the coordinates of 2 points on a plane. All right, so x1, y1 is 1 point and x2, y2 is another point. And what the program is supposed to do is calculate the squared Euclidean distance between the two, which is simply given by the Pythagoras formula. Okay, so you're supposed to calculate the squared Euclidean distance between the two and print that out. Okay. Now notice that here we're not interested in the distance itself, but we're interested in the squared distance. So we don't want to be taking the square root of this quantity. So this is almost the Pythagoras formula without the square root sign, right? And this is the formula that you will be using to calculate the squared Euclidean distance between the points x1, y1 and x2, y2. So here are some hints for this problem. Now use the starter file that is given to you, squared_distance.hmmm, and write your program as 2 parts, a main part and a function part. So what do you need to do in the main part? Well, first of all, read the 4 inputs, x1, y1, x2, y2, representing the coordinates of the 2 points, and read them into registers R1 through R4. All right, so x1 in R1, y1 in R2, x2 in R3, and y2 in R4. Okay, so those are the inputs. And then make a call to a function that is going to calculate the squared Euclidean distance and return the value to the caller, to the main part. Okay, so call the function and write the function such that it calculates and places the desired result, meaning the squared Euclidean distance, in register R5. Okay, so write the function such that it places or computes the result in register R5. Okay, and then the main part simply writes the value of that register, meaning the value of R5, and halts. So that's the responsibility of the main part. What about the function part? Well, in the function, implement this formula for the squared Euclidean distance. So simply calculate the distance using this formula and place the result in R5 and jump back to the column. Okay, so that's it. So that's how you need to implement this program. It's fairly straightforward. Let's move on to the next problem. This problem is called sum of ends, and here you're supposed to write an HMMM program called sum underscore of underscore ends.hmmm that takes a non-negative integer n as input. Okay, so you're given an integer n that is greater than or equal to 0, and all that you're supposed to do is compute and print the sum 1 plus 2 plus 3 and so on all the way up to n. So for example, if this input n is the number, so if n is 5, the program is supposed to compute and print the sum 1 plus 2 plus 3 plus 4 plus 5, so that is 15, right? That's the output that your program needs to print. So let's see how you may want to solve this problem. So here are some ends. First, again, write this program in two parts. Have a main part and a function part. In the main part, read the input n into the register R1, okay, and then make a call to a function that calculates the sum 1 plus 2 and so on all the way up to n and places the result in register R2. Okay, write the function such that it gets its input from R1 and it places the input in R2, places the output in R2. Okay, and then the main part takes over and writes the value of that register of R2, which stores the result, and it halts. Okay, so that's the main part. And now let's see how you would write the function part. So it is in the function part where you implement this formula. Okay, and you're assuming in the function that the input is in register R1 and the output you're going to place in register R2. Okay, and here what I give you is some pseudocode that will do the job. So your responsibility then is to turn this pseudocode into appropriate HMMM code. So let's walk through this pseudocode and make sure that we understand what's going on here, right? So we're going to initialize R2, the result register, with the value 2. Okay, so that's this first line. And then what we do is we check if the input register R1 is 1 or not. If it is 1, then you simply jump to the caller, meaning the main part, okay, because you're done in that case, and the value in R2 is the correct result. But if R1 is not 0, then what you do is you're here, then the first thing that you need to do is increment the register R2 by whatever the value in R1 is. Okay, so take the current value of R2, add to it the value of R1 and store the result back into R2. That's what it means to say increment R2 by R1. Okay, and then what you need to do is you need to decrement the value of R1 by 1, meaning take the current value of R1 and subtract 1 from it and store the result back into R1. That has the effect of decrementing R1 by 1. And then do an unconditional jump to the location in the code given by this label A. Right? So basically jump to that location and then repeat the process. Now as you can see, since R1 is constantly being decremented, at some point this is going to be true, meaning you're going to jump to the column and you'll be done with the function. Okay, so that's the logic, and let's actually get a sense of how this works by tracing it on a small input. So let's say R1, the input to this function, was 3. So you're interested in the sum 1 plus 2 plus 3, which is 6. So let's see how the result is computed. All right, so we're going to keep track of this register R2 as well. So what do we do? In the first step, we initialize R2 to 0. And then we check if R1 is 0 or not. It is not 0, so what we do is you increment R2 by whatever the value in R1 is. So the new value of R2 is 0 plus 3, which is 3. And then you decrement R1 by 1, so R1 now becomes 2, right? Okay, and then we jump to A again and we check if R1 is 0 or not. Well, it's not 0, so we do this line, increment R2 by R1. So R2 is 3, R1 is 2, so the new value for R2 then is 5, 3 plus 2, right? And then we decrement R1 by 1, so this now becomes 1. And then we jump back to A and we test if R1 is 0 or not. Well, it is not 0, so we again increment R2 by R1. So R2 is 5, R1 is 1, so R2 plus R1 is 6. We place the result back into R2, so this is now 6. And then R1 is decremented by 1, so this is now a 0. And then we jump back to A, but now notice that R1 is 0. Okay, and what do? Well, we end up here and we jump to the caller, right? And the caller will go about printing the value of R2, which is 6, and that is indeed 1 plus 2 plus 3. Okay, so this pseudocode here correctly computes this sum, and all that you need to do is translate the pseudocode into HMMM code. Okay. Let's look at the next problem in the project. This problem is called Primality Testing, and here you're supposed to write an HMMM program called primality.hmm that takes an integer n that is greater than or equal to 2. That's the input, and then it's supposed to print 1 if the number n is prime and 0 otherwise. Okay, so you're given a number n that is greater than or equal to 2, and your program is supposed to figure out if it is a prime or not. And if it is a prime number, it's supposed to print the output 1. And if it's not a prime number, it's supposed to print the output 0. Now, what is a prime number? So this hint here gives you the definition of a prime number. So we say that a number n is prime if it is not divisible by any number from the interval 2 through the square root of n. All right. So if you want to check if a certain number, such as 17 is prime or not, all that you need to do is consider numbers I from the interval 2 through the square root of 17, which is as an integer it's 4. All right, so just check numbers from this interval and see if any of them evenly divide 17. If you find such a number, then you conclude that this number is not a prime number. But if you don't find any such number, you say that this is a prime number. Okay. So in this case, 2, it doesn't evenly divide 17. The next number is 3, doesn't evenly divide 17. 4 doesn't divide 17. So you conclude that 17 is a prime number. All right. Whereas any other number, so for example, 26, here again you would try numbers from the interval 2 through square root of 26, which is as an integer 5. So you check if 2 evenly divides 26. Well, 2 divides 26, so you conclude immediately that 26 is not a prime number. Okay, so this is not a prime number, this is a prime number. So that's the idea. So let's walk through the hints for this problem. So here again, split the program into two parts, a main part and a function part. The main part is supposed to read the input n into the register R1. So R1 is like the input register. And then the main part simply calls the function that calculates the desired result, meaning it's going to place the result of 0 or 1 in the register R2. So R2 is like the output register for the function. And a value of 1 in R2 would mean that this number is a prime number. And a value of 0 in R2 would mean that this is not a prime number. Okay? And then the main part simply writes the value of R2 as the result and hearts. So the main part is rather simple. Now let's look at the function part and see how it actually tests if a given number is a prime or not. Okay, so the function part expects its input in the register R1. Okay, and it's going to place the output, which is 1 or 0, in the register R2. 1 meaning n is prime, and 0 meaning n is not a prime. And here is the pseudocode that implements the algorithm that can figure out if a number is prime or not. So let's walk through that carefully. So the first thing that we do is initialize the register R3 with the value 2. So R3 is going to store the potential divisors of n. All right, it's sort of like this I here. Okay, so I stores all the potential divisors of n. Right. So we start R3 with the value 2. And then R3 is going to become 3, 4, and so on, and it's going to take on values from the interval 2 through square root of n. Okay? And then we test if R3 is strictly greater than the square root of n. And if so, what we do is we conclude, okay, that the number R1 is a prime number. So we place the number 1 in R2 and we jump to the column. Because what does this mean for this condition to be true? It means that you didn't manage to find any number from the interval 2 through square root of n. So R3, you didn't manage to find any R3 from this interval that evenly divides n, from which you conclude that n is a prime number. And that's what you're doing here. So if this condition is true, it means n is prime, so you place the result 1 in R2 and jump to the column. But what if this condition is not true? So if this condition is not true, then what you do is you check if n, which is stored in R1, is evenly divisible by the current value of R3. Okay, and this is where you need to make use of the mod instruction to test if something evenly divides another number. Okay, so you test if R1, meaning n, is divisible by R3. If so, what you do is you conclude that n is not a prime number, because you've managed to find some number, some R3 from this interval that evenly divides R1, meaning n, right? So in that case, n is not a prime number. So what do? We simply set R2 to the value 0 and jump to the collar, saying that R1 is not a prime number. But what if the current value of R3 does not evenly divide R1? Well, then you cannot right away conclude that R1 is a prime number. You have to test the next value for R3, okay? And that's what we do here. So if this condition is not true, meaning if R3 doesn't evenly divide R1, we consider the next value for R3. So we increment R3 by 1. So R3 starts at 2, it becomes 3, and then 4, and then 5, and so on, okay? And then we simply jump unconditionally to A, which is this part of the code, all right? And repeat the whole thing again, all right? Now, as you can see, since R3 is constantly being incremented, at some point it's going to meet this condition. So this condition is going to turn out to be true, in which case we end up here and conclude that R1 is a prime number, meaning we didn't find any number from this interval that evenly divides R1. Okay? So that's the logic. Now, there is some thing that I need to, one thing that I need to clarify, which is this part here that is indicated by this dagger symbol, which is explained right here. Right? Now, how do you test if R3 is greater than square root of n? All right? You really don't have direct instructions for that. You cannot calculate the square root of a number in HMMM, right? And then you cannot test if the value in a register is greater than any arbitrary value. That's not available either. Instead, you have to seek a workaround, and that's what is explained here. Okay. So saying that R3 is greater than square root of n, I hope you guys see, is the same thing as saying R3 square is greater than n. So how did I go from here to here? Simply squared both sides. Okay, if this is greater than that, the square of this is greater than the square of that, which is what we are saying here. Now this thing is the same as saying R, right? So all these expressions are equivalent. So saying R3 is greater than the square root of n is the same thing as saying R3 square is greater than n, which is the same thing as saying R3 times R3 is greater than n, which is the same thing as saying R3 times R3 minus n is strictly greater than 0. Okay, I just took the minus to the left hand side and we have this. Now this is something that you can implement in HMMM because you have all the necessary instructions. Okay, so this that you see in the pseudocode here really needs to be implemented as this. Okay, so that's basically the idea. Okay, now let's move on to the next problem. This problem is all about calculating the GCD, or the greatest common divisor of two numbers, using Euclid's algorithm in an iterative way. Right? So here we are supposed to write an HMMM program called GCD_iter that takes two non-negative integers x and y as input and simply prints their greatest common divisor, right? Which is the largest a number that evenly divides both an x and y. So for example, if x is 6 and y is 9, what is the GCD of x and y? Well, it's 3, because 3 is the largest number that divides both 6 and 9, right? So the GCD of 6 and 9 is 3. Alright, so here we're going to use a classic algorithm called Euclid's algorithm, and we're going to use it in an iterative fashion, right? What does the algorithm say? Well, the algorithm says if y evenly divides x, then the GCD of x and y is simply y, right? Otherwise, what we say is that the GCD of x and y is the same as the GCD of y and the remainder of x and y. Okay, so let me repeat. If y evenly divides x, we simply conclude that y is the GCD of x and y. But if y does not evenly divide x, then we say that the GCD of x and y is simply y, the GCD of y and x mod y. So in the next iteration, y takes the place of x and x mod y takes the place of y. Okay? So this is what we need to arrange when we do our calculation. So let's now go through the hints. Again, split your program into two parts, a main part and a function part. In the main part, read the two inputs x and y into registers R1 and R2 respectively. All right, and then make a call to a function that calculates the GCD of those two numbers and places the result in register R3. And then the main part is going to write the value of R3, meaning the result, and halt the program. So that's the main part. Now let's look at the function part. In the function part, we expect the inputs to be in registers R1 and R2. So that's x and y, x in R1 and y in R2. Okay. And the result is going to be placed in R3. So R3 is going to store the GCD of x and y. So let's see how it's done in pseudocode. So the very first thing that we do is check if R1, meaning x, is evenly divisible by R2, meaning y. Okay? And if that is the case, we're here, what do? We simply say set R3 to be the value of R2. So simply assign y to R3, meaning y is the GCD, and jump to the caller. That's basically this part. If y divides x, then the GCD of x and y is y. Okay. But what if y does not divide x? In that case, this is not going to be true, meaning R1 is not divisible by R2. So we end up here, and this is where we say that the GCD of x and y is the GCD of y and x mod y. So the new value for x is whatever the value of y is, and the new value for y is the old value for x, which was in R1, remainder y. All right. So that's what we need to do. So we need to make x be the current value of y, and we need to make y be the remainder of the old value of x and y. Right? And that is explained later on here, right? And I'll get that in a bit. And then once we do that, we simply jump unconditionally to the point in the code that is given by this label, right? And we repeat this process. Okay. All right. Now here, this part of the code that is marked by this dagger needs some care, right? You cannot simply assign R2 to R1 and then R2 to R1 mod R2, because here the value of R1 that we need is the old value before this assignment. Okay, once you say R1 equals R2, then R1 has changed. We don't want that. So in this calculation here, R1 needs to be the old value of X, right? So the way to correctly implement this is using this approach, right? So first store R1 in some temporary register, let's say R4, okay? So that's the value of X stored in R4. Okay, and then we say the new value of R1 is simply whatever R2 is, which was Y. So R1 is now Y. Okay, and then we say R2 is basically the remainder of R4 mod R2. But what was in R4? The old value for X. Okay, so that's X mod R2, which is simply Y. And that's exactly what we want. Right? So we want R1 to be Y and R2 to be the old value of X, remainder Y. Okay. So that's how you need to implement this part. Okay? All right. So that's how you handle this problem. And the last problem is implementing Euclid's algorithm, but using a recursive approach. Okay. So here you need to write an HMMM program that is called GCD_rec that takes two non-negative integers X and Y and prints their greatest common divisor calculated using Euclid's algorithm, but recursively. Okay, and here is the recursive definition for Euclid's algorithm. So we say that the GCD of two numbers X and Y is simply the GCD of Y and X remainder Y if Y is not 0. Okay, so if the second argument is not 0, then we make a recursive call to GCD with the arguments Y substituted for X and X remainder Y substituted for Y, right? That's the recursive step. But what if Y equals 0? Well, in that case, the GCD of X and Y is simply Y. Okay, so let's take an example of this. So GCD of, let's say, 6 and 14. So X is 6 and Y is 14. What is this? Well, Y is not 0, so this is going to be GCD of 14. So Y takes the place of X and the remainder of X and Y. So what is the remainder of 6 and 14? It is simply 6. Now notice that X is 14, Y is 6. So this results in GCD of Y, which is 6, and the remainder of 14 and 6, which is 2. This now results in GCD of 2 and 6 remainder 2, which is 0. And now we are at the base case because Y now is 0, and this simply ends up returning the value of X, which is 2, and that is indeed the GCD of 6 and 14. Okay, so that's how Euclid's algorithm works. So now let's see how we implement this. So here again, write your code in two parts, a main part and a function part. Now in the main part, since this is a recursive implementation, what we need to do is first set up the stack pointer, right? Because we need to make use of the memory to create a stack, to build a stack. So set R15, the stack pointer, to the location 100. And then go about reading the inputs X and Y into two registers R1 and R2. Okay, and then make a call to the function that calculates the desired result, meaning the GCD of X and Y, and places the result in R3. And then finally, the main part needs to write the value of that register R3 as the result and halt the program. So that's what the main part needs to do. What about the function part? Well, here's the pseudocode for the function. The function expects the inputs to be in R1 and R2. So X is in R1, Y is in R2, and it's going to place the result, meaning the GCD, in R3, and then jump to the column. So how does it do its job? Well, we first check if R2 is 0 or not, meaning is y 0. If it is, then we are at the base case, so that's this part, right? So if y is 0, we are at the base case. So in that case, we simply need to place the value of x, which is in R1, in the result register R3 and jump to the caller, okay? So that's the base case. But what if R2 is not 0? In that case, we need to make the recursive call, so that's this part. So how do we do that? Well, we first increment the stack pointer by 1, so that's that line, and we store the return address R14 in memory at that location R15, right? Okay, and then we need to do this. So we need to set R1 to be the value in R2, and then we need to set R2 to be the old value of R1 mod R2. So here again, you need to use this idea to implement this part, all right? So set R1 to R2 and then R2 to be the old value of R1 remainder R2. And then make a recursive call to the function whose definition starts at A. So that's the recursive call, right? And then when the recursive call returns, what you need to do is load the value in memory at R15 into the register R14. Okay, load the return address from memory into R14 and then decrement the stack pointer by 1, right? And then jump to the caller, right? Jump to whatever the location is that is given by R14. Okay. Now here again, notice that this value R2, since we are calculating it as the remainder of R1 and R2, R2 is going to constantly shrink, right? And it's eventually going to become 0, which means at some point the base case is going to be true, and in which case we set the result register R3 to R1 and jump to the caller. Okay, so this recursion is eventually going to terminate, which is what I'm saying. All right, so that's how you need to implement this program. Again, the pseudocode tells you exactly what you need to do, right? All that you need to do then is to translate this diligently into HMMM code. And then if you do that, you should have your program do the right thing, okay? All right. A few final comments. Now, make sure you write a report for the project. And when you do that, make sure you use the template that is given to you. Okay, report.txt. That's part of the zip file that you downloaded for the project. And now in that report that you write, make sure you specify the time that it took for you to work on this project. Give a short description of how you approached each problem. Do talk about the issues that you ran into and how you solved those issues. And then if you received help from anyone, please acknowledge that, and that's extremely important, right? Any help that you receive from anyone needs to be acknowledged in your report, okay? And then also give us some other comments, such as whether or not you learned anything from the project, whether or not you enjoyed working on it, and so on, right? So that's something that we would like to know. All right, and then before you submit your files, make sure that your programs meet the input and output specification. All right, that's extremely important. You might think that your programs work fine, but then when you turn it in on Gradescope, they might not go through. Okay, so to avoid any such issues, just once you're done with the problem, just run this script, the run test script, okay, which will test your solutions and make sure that they conform to the input and output specifications. So the way you test a particular problem is by mentioning that problem number here, such as problem 1, for example, in which case run test will test exactly that problem. You can test multiple problems by just listing them here, separated by commas, in which case run test will test each one of those. Separated by spaces, and then run test will test those problems. And if you don't specify any argument, run test is going to test all the problems. Okay. And then finally, make sure that your report is not too long. Make sure that it doesn't contain lines that exceed 80 columns, because that makes it quite unreadable. And then finally, make sure that your reports are relatively free of spelling mistakes and grammatical mistakes, right? Okay, so that's what I had to say about the problems in Project One, and hopefully, I've given you enough hints to get you going. All right. I hope you enjoy the project, and thanks for watching this video.